Hi, it's Terry Dennery of the MathWorks. So in the last video, we did our vertical takeoff. We got it working really well, right, and precisely moved the way we wanted it to. But what we saw was an incredible sensitivity to our data, our information, where that center of mass was. And so it was, this is a vehicle that's perhaps like 2 meters long, and we saw a real sensitivity to mispositioning of less than a millimeter. All right, so I'm going to reproduce that right now. So we've been using this data file, and basically we saw we had to add the last 3 numbers. We didn't really measure it real well and see if we just needed to add 1 more or 2 more or whatever. But certainly at this point we're less than a millimeter with these numbers, and so almost 1/10 of a millimeter. So anyways, that just kind of made me realize, well, let's put a little bit of the feedback control discussion into this right now. I was probably going to do this a little bit later. So anyways, just to remind you of the error, we'll run it again with the less resolved number for this. So let's go here. Let's hit run. And we'll watch that same simulation. I think you see it pretty quickly. It starts moving forward very quickly, and certainly here you can see that downward pointed angle. Okay, and with that, kind of nose down and vertical thrusters being applied on it, the vertical thrusters got kind of a side component, which will then, of course, accelerate it in the horizontal direction. Right. So here's kind of what I came up with. You can see a new kind of line in this, and you can see it works too. Let's go ahead and hit run. I'll show you that, yes, indeed, this will work. Right. So based on that same mispositioning, we're able to hit that vertical takeoff again perfectly. Okay. And basically this thicker line represents, I'll call it, more data is coming across. And so we're going to have something that I call the front-rear displacement. And basically it's a vertical position difference between the front and the rear thrusters. And it's a good measurement of tilt, and that's why I like it. And then I just operate on that directly with the PID. I don't even do like moment arms or anything like that, because this is a PID. And one of the kind of cool things about PIDs is you just kind of need the general, I'd say, driver of things, and constants will just kind of work themselves out in what your PID gains will be. Okay, so anyways, so this video is really about how did we get here, right? And I'm going to go into here and I'm going to borrow one thing I did, and that's the measurement of the front and rear displacement, right? And so let me go ahead and copy it. I'm going to show you a little bit. All right, but basically for all those local, or I'll call those nodal positions of where the thrusters, idealized force acts, that we're going to measure position just like we did for our overall elevation measurement. We use this block to do it. It's essentially with regard to a world reference, we measure X, Y, and Z. All right, and so we do it for all of them. We get the Z components with all these, and we do the math of averaging kind of the rear thruster kind of vertical position and doing the same for the front, noting that there is a 0.15 meter offset between the two. We're able to essentially define a really nice error signal through this, right? And so let's copy this and we'll paste it in to this model, right? So let's go in here. Let's go ahead and get that. We don't need that anymore. That was that constraint we used in our initial modeling of vertical takeoff. And we talked about removing it in the last one. All right, so let's paste this in like this, and then it's just a matter of connecting into those nodal positions. Okay, now that feedback, you saw it with the thicker lines, well, that's what we call a bus. And so now we want to really kind of deliver a couple pieces of information in our feedback. And one will be the center of mass position of the full vehicle. Should do this in between videos, but let's see if I got it. Yeah, it's not bad. All right, and so we still want that, and then we want this as well. And so I'm going to introduce a bus creator. Let's make it bigger. Okay, and so let's take that data right there, and let's take this right there, and basically we name the signals. And so I'll just call this CM for center of mass position. Zoom in a little closer so we can read that. And I'll call this, what, again, it's, you might say it's my temporary name, but I might just stick with it. Some naming can be hard, so let's go. Okay, let's double click here. Sometimes technically naming can be hard. I'm trying to get the little blinker so I can name this right now. Oh, it's already there. Oh, and it kept it from the other file. All right, so let me zoom in. So when I brought this block in, it knew the signal coming out. This is just a convention of Simulink. It's going to be called FR displacement. So, anyways. And so this names come in, and this is a bus, and it's very much like a MUX block, with regard to that we're carrying multiple signals. But I kind of like that they have names, right? And so this will now be our feedback, and I kind of like this term when I do these things. All right, so we're going to make this an output from this block, and so I'm going to call this M bus. We'll send that in like that. Okay, and when I bring something all the way up to the top, kind of like copying the output block names or the output blocks themselves and just pasting them in on the way up. And so then come up here. As it realizes a change has been made, I'm going to kind of just delete all that for right now and paste this. Oops, I don't need to have it at this level. But what I do need to do is kind of pull out the information, because this is now carrying more than what used to go in there. So this is a bus selector. Okay, now we come in here and we select what we need. And certainly we will not go for any of those generic signals. Bring in the position at this level, and we will put this block. Okay, all right, and so here we measure CM position and just plop it in right like that. All right, and now we'll take this and apply this feedback. It's fine, it doesn't get thick until we actually hit run, so we'll see that in a moment. All right, and I'll just kind of prove it still works. It at least works, with that incredible sensitivity to the center of mass position, which is what we're going to fix in a moment anyway. So, and you'll see that we're basically getting the same simulation that we had before. We do have that forward movement. All right. Okay, so forward thrust components, rear thrust components. All right, and you might recall how we had to change their orders, and we did that. Oops. But I know the top is forward, bottom is rear. All right, and so I'm going to go in and get that FR displacement. We'll add that as part of the output. All right, and now I'm going to type in PID library, but from Simulink. There you go. right? And so the PID is going to, essentially FR displacement is an error. It's going to operate on that. And what it's really going to do is going to come up with, I'd say, the force components that will generate the moment that will correct this, right? And so up here, I'm going to put in some blocks. And so I'll put one there to receive some force for the forward or front thrusters, one here to receive some forces for the rear thrusters, right? And so we're going to take that same signal in for both of them, and we're going to just do one. Okay, so it's adding to what's been calculated theoretically by all this. And the one last piece is that if it's tilted up a little bit, FR displacement will be positive, and it actually means that we want a little negative force, on the top. And so the last piece to this, I think this will work pretty well. Is we'll make that a minus. Okay, and let's hit run. And we'll get to tuning gains in a second. I don't know if you can notice, but it looked a little bit better to me. And it certainly isn't as bad. You can even see kind of the underdamped oscillations are going on with the PID. And that's merely, kind of a tuning thing. And so let's get in here. We did this with the default values of 1, 1, and 0 for KP, KI, KD. And certainly a very good feature that I like to show people all the time is the tune button in the PID block. And so what it's doing really is kind of sampling the model itself, the response of the model, and essentially constructing kind of all the formulations and I'd say, things like Bode plots, root locus, whatever, kind of methodology to come up with, more ideal tuning, it is now being used. And I kind of look at this immediately, like, oh, that looks pretty good. But then you look at the time scale on that, and I'm like, ooh, that's not fast enough. I can't wait 14,000 seconds. That's the response. And I'll just say that with regard to tuning, maybe the initial answer is delivered kind of cautiously. And so we got very, very small gains here. And so what I'm going to do is just kind of speed it up and just kind of continue to check and make sure things are good. And so I am going to keep on going until maybe I get something under a second on response. And let's perhaps go one more time, right? And with that, I think let's go one more, right? And kind of the methodology in general that I like to promote is use what you know, like we did in the previous video. So if you know how heavy it is, that's helpful. If you know moments, all that kind of stuff, positions of thrusters, that's good stuff. And what it tends to do is kind of minimize what your errors could be anyways. And in the way it allows you to be a little bit more aggressive in what you're going to use for your gains. So anyways, perhaps I was a little bit aggressive here, but let's just kind of go with it. And I'll hit update. And that's our response now. And update kind of filled those numbers into my controller right there. And I'll click on OK. And I'll hit run. And we'll watch it one more time. Okay, so I'd say again that's nearly perfect, and so through those PID controls, all of a sudden you don't have this incredible responsibility to understand, like positional things at a sub-millimeter level, for a vehicle that's like 2 meters long. So anyways, I don't think airplanes could fly without feedback control, and certainly we came up with a good example where we needed to include it. So thank you very much. See you on the next one.